Hey guys, so this is our last lab coming up, and because I didn't give you guys a lot of heads up as to what we're doing, I'm making a quick little guide here on some of the calculations as well as some of the theory that we're doing, because this is a, like make your own protocol type deal. You're going to approach this in the exact same way that you approached vitamin C, as far as, how you're determining the concentration of ethanol in your samples. Again, if you don't want to bring a sample or you don't feel comfortable with that or you're not 21 or whatever, I'm going to bring in a PBR and you can use that as your sample. Um, but okay, so let's talk a little bit really quick about just what exactly we're looking at here. So basically, there's this enzyme called alcohol dehydrogenase that will take an alcohol and convert it to an aldehyde or a ketone. In this case, this is going to be acetaldehyde. That's what this molecule is called. To do this, it requires an NAD plus cofactor. And what that's going to do is it's going to basically accept a proton from this oxygen, which will then, you can imagine, those electrons can knock down there and generate this aldehyde. Okay, this aldehyde is pretty unstable. And so the acetaldehyde, so we're going to basically, this is called in, like organic chemistry, we'd call this a trapping reagent. But basically, this is a pretty reactive guy right here. And so, or a pretty unstable thing. It also might evaporate. So we're going to trap it with this molecule here, which is I can't remember exactly what it's called. I haven't seen this chemical before, but it's all in your protocol, and really all you need to be concerned with is that we're going to be trapping it with this molecule to yield this more stable product. But the way we're looking at this reaction is actually by the appearance of the signal for NADH. So as you can see here, this is a conjugated molecule with this positively charged nitrogen, allowing you to have a pi system here with a Huckel number of 6, right? Now you only have 4. So it's an anti-aromatic system. It's going to have a different absorbance behavior. And this is where the actual proton is getting accepted. But this NADH here absorbs more strongly at 340 nanometers than does NAD+, which barely absorbs at all. So we're going to be looking for the appearance of that signal. Now, you can imagine that as there's more alcohol present, if this is, a one-to-one stoichiometric oxidation of the ethanol, meaning for every one molecule of ethanol you have, you'll oxidize that down to one molecule of acetaldehyde, and you'll also be generating one molecule of NADH. Then we can use the appearance of this signal to quantify how much ethanol is there. The way we're going to do that is with, like we've done 1,000 times now, a standard curve. So we're going to build a standard curve of known ethanol concentrations. We're going to get some sort of line, and then we will compare unknown samples to that. Now, you can imagine that as there is more ethanol around to be oxidized, you're going to have more NADH. So we should see a line that looks like this with a negative slope with the highest concentration of ethanol values, which will be your x-axis, giving you the highest signal at 340 nanometers. Okay, so the way we're going to build the standard curve is by taking a standard of ethanol, and just like we have with so many other things, building a standard curve of known concentrations versus some signal we're looking for. In this case, it's going to be the absorbance at 340 nanometers. Okay, so all we're going to do here is just to M1V1 our way to greatness. So what I have here is I have the stock concentrations listed in these table headers here, as well as the desired concentrations down here. This one is a little bit different for the concentration of ethanol. You've already actually got it right here. And you can change these values up a little bit if you want, but no real need to. Okay, so let's get going. First of all, our final volume is going to be 250 microliters. So that is our V2. This is going to be our M2. This is our final concentration. And we have our M1 given here. So all I'm going to do is M2 times V2 divided by M1 will give me V1. So say equals M2, I'm going to do Control or Command T on Mac to do an absolute reference. M2, or excuse me, V2 times M2. Again, I'm going to do an absolute reference there. And then I'm going to divide that by my M1, which is 150. And this is going to be the same for all of my samples because this concentration of buffer is going to be the same. So again, all I did to do that was I double clicked this little fill handle, or you can pull it down. It'll do the same thing. And because I held absolute references with these dollar signs here, it's going to keep referencing these. If I didn't hold the absolute reference, which I'll show you here, say I did that, Okay, it's going to just start to, oops. Here. If I pull this down, it's going to start getting confused and it's going to be referencing, things that are all over the place. So we don't need to do that. All right. That's how you do this. And in the same way, you're going to solve these other ones. I'm not going to solve absolutely all of these just because that would be kind of counterintuitive. But again, I'm going to do V2 times M2 divided by our V1 is 3. Okay, sick. Yeah. You'll do the same thing here. If we are starting to go over volume, meaning this is getting above 250, we might need to use more concentrated stocks of stuff, and we'll fight that battle when we get there. I just want to make sure that this ethanol is sound. It's not going to go over volume here. So I'm just going to solve one of these in completion. I'll show you how I do that. So again, V2 times M2. In this case, I'm not going to use an absolute value or an absolute reference because I want to, as I pull this down, I want this cell to reference this cell. And then when I pull it down, this one to reference this one while still holding the same volume. And it wouldn't be the end of the world if I did an absolute reference here because it would just keep reading down. Whatever. Okay. And then dividing by my M1, which is 2 millimolar. Okay. All right. Sick. Let me just calculate this out real quick, just to make sure we're okay. Sorry, times M2. Oops. Sorry about that. Just go back here, times my M2, and then divide that by M1. Okay, so now all I'm going to do is I'm going to say for the volume of water, it's just whatever I need to do to get up to 250 microliters. So I'm going to say it's this. You can absolutely reference it or not. It doesn't matter because these are all the same. Minus, and I'm going to say sum. This is the easiest way to do it. Say sum. I'm going to hit tab, and then I'm just going to highlight these and then close the parentheses. Oops. And then I'm going to do it wrong. And I'm going to just pull this down. And you can, this is obviously you can't pipette 14.166666667. So you can just reduce the number of decimal places to something you actually can't pipette like this. If you don't want to do the sum thing, if that confused you there, you can just say, I want it to be the total volume minus this plus this plus this plus this, which is totally fine. It'll still give you the exact same data. Look at that. Wow. Ignore that. Okay, so I guess I just did everything for you. So that's great of me. But yeah, just make sure you know how this works. Again, if you don't want to have 83.333333333, you can just reduce that down like that. Okay, so yeah, I just did all the work for you. But make sure you know how to do this because Excel is useful. And I will see you guys in class. I'm going to stop recording now once I figure out how to do that, even though I've done this so many times. Here we go. Okay, bye.